Hi everyone, I have an interesting limit problem for you. It is the limit n goes to infinity n times sine of 2n factorial times e times pi. Well, first of all, I know that sine function has the period of 2 pi, so if I take any multiples of 2 pi and add it to a number, here the k is an integer, this is going to be equal to sine of n. So if I take the integers part of n factorial times e, because I have 2 pi here, I can try to separate it as like integer parts and fraction parts, and I will have something a bit more simplified. So n factorial times e, let's make another reminder that e to the x has the series expansion of n greater or equal than 0, x to the n over n factorial. This converges for all x complex numbers, so we can just put x is equal to 1, and this is going to be equal to n factorial times 1 plus 1 over 1 factorial plus 1 over 2 factorial plus it goes on like this. And I'm writing few more terms, and let's see, why did I write it like this? Because I'm multiplying everything by n factorial, and if I multiply up to 1 over n factorial, all of these stuff will give me an integer. So this is equal to 1 plus, I'm writing the first part alone, and I'm separating the other part, 1 over n plus 1 factorial, and it will continue till infinity from this point. And now, if I call this part an and this part bn, I know that an is an integer because all of these terms has less factors than n factorial. So this is equal to k, let's say it's equal to k. So now, if I get back to the question, sine of 2 pi n factorial times e, this is going to be equal to sine of, so I said that n factorial times e is equal to an plus bn, 2 pi an plus bn. Now I can just separate this 2 pi an part because now it's like k. So I can just take the fraction part, which is equal to sine of 2 pi bn. So we will use this later. Now let's find upper and lower bounds for bn. So I know that bn is equal to n factorial times 1 over n plus 1 factorial, 1 over n plus 2 factorial, and it will go on like this. So if I multiply it, I will get, they will just simplify, n plus 1, plus 1 over n plus 1, n plus 2, and it will go on like this. Finding a lower bound is easy because all of these terms are positive. So I can just say this thing is greater than 1 over n plus 1. This is greater than 1 over n plus 1. And for the upper bound, I know that n plus 2 is greater than n plus 1. So if I take reciprocals of it, this is going to be equal to 1 over n less than 1 over n plus 1. And if I multiply both sides by 1 over n plus 1, I will get this thing, and this is going to be less than 1 over n plus 1 factorial. Not factorial, 1 over n plus 1 squared. So I'm just writing the first term like this. And so, as I said, this thing is less than 1 over n plus 1 squared. And if I continue like this, the next term has the, at the denominator, it has 1 n plus 1, n plus 2, n plus 3. So this is going to be less than 1 over n plus 1 cubed, and it will go on like this. So if I take 1 over n plus 1 parentheses, this is a geometric series, and so it's 1 plus 1 over n plus 1 plus, and the ratio is 1 over n plus 1, which is less than 1. So this geometric series will converge, and it will converge to 1 over n plus 1 Actually, we can say this is equal because we have up to infinity 1 over n plus 1. So it is going to converge to 1 over 1 minus, and this our ratio, so it's n plus 1. And so this is going to be n over n plus 1, and we will just flip it, so it is going to be 1 over n plus 1 times n plus 1 over n, which is equal to 1 over n. So we found upper bound 2. We found that 1 over n plus 1 is less than bn, which is less than 1 over n. Cool. So now let's get back to the question. We said sine of 2n factorial times p times e, and we said this is equal to sine of 2 pi bn. And actually in the question we also have n, so let's put also n's. And now let's see what we can do with the limits. Limit, I'm taking limits. So this is the statement were given in the question. So I will just continue from this part. So this limit is equal to n times sine of 2 pi bn. So if I look from here, like what would happen if I take limits of all sides? This part would be 0. This is also 0. So by the squeeze theorem, limit as n goes to infinity, bn is going to be equal to 0. So I have something here that the inside of sine goes to 0, and I actually know something close to that. Limit x goes to 0, sine x over x is equal to 1. This is one of the most popular limits. And so I have something here. We can think about this x as anything that goes to 0. Okay, so here bn goes to 0 as n goes to infinity. So if I multiply it by 2 pi, it's not going to matter. So this inside will converge to 0. So I'm going to divide it by the x. Here it's 2 pi bn. And I of course need to multiply it back again. 2 pi times bn. Let's also call this limit L. So now what I'm going to have is that limit. Let's try to separate it. I can't separate it right now, but we will see now. 2 pi bn over 2 pi bn times, so for the rest I have 2 pi and bn. So now let's go up, and what would happen if I take limits of n bn? So I'm multiplying all sides by n. Okay, this is n, and if I take limits, this limit is 1, this limit is, I don't know, this limit is also 1. So again, by the squeeze theorem, I would get that limits of n times bn, this limit is going to be equal to 1. So now I know that this limit exists because this limit exists, and this is just an integer. It's just a constant, sorry. And I know that this limit exists, so I can separate this limit. Limit n goes to infinity. I can separate two limits only if and only both of them exists. So it's going to be equal to sine of 2 pi bn over 2 pi bn times limits of n goes to infinity 2 pi and bn. Now let's finish it up. I know that this limit is 1. I just explained it. It's like a sine of x over x. And for this part, I said that this limit is 1. So this is just a constant. I can take it before. And so it's going to be equal to 2 pi times 1, which is equal to 2 pi. And this is our answer. This limit is equal to 2 pi, and that's it.